Good afternoon, everyone. My name is Gokulanand, and today I'll present our fabrication and characterization of cellulose-based materials for biodegradable soil moisture sensors. And this work has been supported by the IEEE and is an engineering research firm. So, with the global population projected to rapidly increase over the next several decades, increasing agricultural output to meet this demand has become a global challenge. Internet of Things has been proposed as a solution to meet this demand. By collecting sensory data on the field, we can spatially and temporally monitor key field variables, such as nutrient concentration and soil moisture, and use that data. So farmers can essentially use this data to effectively deploy the resources and use them as and when needed. However, in order for this technology to be practically implemented and scalable, the sensors that are used need to be inexpensive, biodegradable, and provide fine-grained enough data that actionable measures can be taken based off of that. In order to address this, we at the IEEE and the Engineering Research Center are developing low-cost, passive, biodegradable sensing platforms that we can use for developing substances. So shown here is a schematic of what the envisioned sensing protocol is. And so I'll talk about the sensing protocol a little bit, but just as an overview, the main elements are the antenna, the acoustic resonator, the sensing element, and then a biodegradable substrate that all of this is built on. And so in my talk today, I'll be focusing on two elements of this schematic, specifically the substrate and the sensor. So I'll talk about the work we've been doing to develop a biodegradable, completely biodegradable substrate for developing such sensors, as well as the interdissociative capacitive sensing element we've developed that leverages the properties of the substrate to enable moisture responsive sensing. And so the objectives of this work were to, one, develop a biodegradable cellulose substrate that we can combine with screen printing to repeatedly fabricate high-quality electrical structures, to fabricate a capacitive moisture sensor on this substrate and show that it can operate at our frequencies, specifically the 902 to 928 megahertz band, the ISM band we want to work in, and then to characterize the electrical properties of the substrate under varying ambient moisture conditions, which here we do so using by changing the humidity. And so just to give you a little bit of background, there are several soil moisture sensors available on the market. So in this work by Fabrication, for example, they evaluate the use of an off-the-shelf capacitive soil moisture sensor for measuring gravimetric water content. Similarly, in work by Kojima et al., they evaluate the use of network-connected capacitive sensors that are based on PVC pipes for getting spatial soil moisture data. However, these sensors and others like it require constant maintenance, are large, not appropriate for scalable application, and are non-biodegradable. There's been some work done on developing sensors based off of cellulose-based materials, such as in this work by Kim et al. However, the cellulose-based materials that are used in this and other works often contain plastic fillers. So most cellulose-based substrates are formed from highly porous and rough surfaces, and so plastic fillers help to planarize the surface and make them appropriate for developing sensors. However, such materials are not biodegradable and therefore not appropriate for agricultural applications. So to test this, there's been some recent work done on using cellulose nanofibers, or CNFs, for developing smooth paper-based substrates that are completely biodegradable. And there's been some preliminary work on developing sensors using these materials, such as this work by Iyer et al. But before I continue talking a little bit more, I wanted to talk about cellulose nanofibers. So cellulose nanofibers, or CNFs, as I'll refer to them from now on, are high aspect ratio fibers that are derived from cellulose. So shown here on the right-hand side, this image is a TEM image of a solution of CNFs. And as you can see, there are these high aspect ratio long fibers. And so when you take CNF solution and you either dish dry it or you use vacuum filtration to dry it, you get these really smooth and transparent films, as can be seen here. You can see the pen logo through it, that are very smooth and transparent. But the problem is that pure CNF sheets are very brittle and they're very expensive to fabricate compared to traditional pulp-based papers. So the question becomes, how do we get the beneficial properties of CNFs at a more economical cost? And so to address this, we've developed a CNF-infused cardstock composite that makes minimal use of CNF solution, but still gives us these really smooth surfaces. And so the way we fabricate these composites is that we take the cardstock and we coat it with an initial layer of CNF solution. We allow the solution to partially infiltrate before applying the second layer to build up the CNF layer. allowing that to partially infuse, and then we heat press the sample and allow it to dry in the oven. And the result are we get these really glossy and smooth substrates, examples are shown here. And so the benefit of this is that we get this really smooth planar surface by making minimal use, around 25 grams, for example, of CNF solution. And so now that we have these smooth surfaces, we wanted to kind of see how do they actually compare surface-wise to just plain cardstock. And we did this by under SEM. And so on the left-hand side here, we see, as I mentioned before, that the surface of the cardstock is comprised of these highly porous entangled microcellulose network, which gives it a very rough surface. But by infusing it with a CNF solution, as we see on the right-hand side here, the porosity is greatly decreased, and we get this smooth, continuous film that is suitable for printing sensor. And so, moving on from this, we wanted to evaluate, okay, we know these materials smooth, what are the quality of the traces we can print on these? And so we use screen printing to fabricate silver ink-based electrical structures on the CNF composite, as well as in cardstock and polyimide. And so in the center here, we can see that the structures print on cardstock, because of the surface roughness of the substrate, we get these really jagged edges on the structures, and it's not of the quality we want for developing sensors. Compared to the traces that we see printed on the CNF composite, we see that we get these smooth edges, and they're of comparable bait quality to those printed on the polyimide substrate, which is encouraging. But we wanted to quantify this to see, okay, how smooth are these and repeatable are these structures? And so to do this, we employed surface profilometry to characterize the surfaces themselves as well as structures that are printed. And so to do this, on the left-hand side are the surface profilometry of the CNF composite, the cardstock, and polyimide. And we see that the surface of the cardstock is highly has an RMS roughness of about 3.46 microns, but that the surface roughness of the CNF composite is comparable to that of polyimide. And we can see from the RMS roughness that we calculated that they're very close, which is very encouraging. And we see that this translates to highly repeatable and consistent structures that are printed on the substrate. And again, you can see that there's a great variability in the traces that are printed on the cardstock. We see high repeatability and consistency of the structures that are printed on the CNF substrate, and there's comparable quality on polyimide. So with this, we're very encouraged that we can repeatedly print these structures. The next step we wanted to do was to actually print the sensing element and to evaluate the response of the sensing element. But before I do that, I wanted to give just a brief outline of what the passive sensing protocol we're using is. So here we have a transmitter shown as a drone here. It emits a multi-frequency signal that is received by the antenna. The RF energy is stored in the acoustic resonator that has a resonant frequency of F0. And this resonator is connected to our integrated capacitor. So nanocellulose is very moisture responsive. And so as it's exposed to environments with varying amounts of moisture, the dielectric values of the substrate change. And therefore the capacitance of the sensor here will also change, which will pull the resonant frequency F0 of the resonator. And then by looking at the difference between the emitted and re-radiated signal, we can get information about what the ambient moisture of the environment is. And so to characterize this, we printed 1 picofarad capacitive structures on the CNF composite, as well as on cardstock and polyimide, as shown here. And we did electrical characterization using a custom 3D printed humidity holder in a probe station using ground probes. And we did a frequency sweep and looked at the equivalent capacitance as for 3 different humidity conditions. And so first, looking at the data that we saw for the polyimide and plotting it, we see that as we increased the relative humidity, we saw little to no change for the structures for polyimide, which is not surprising as polyimide is not moisture responsive. So the next thing we did was look at the data for the cardstock. And so initially, as we went from 35% relative humidity to 57% relative humidity, we saw this spike in the capacitance because microcellulose has these pores that can uptake moisture. But we saw that as we further increase the relative humidity, the response saturated and we weren't able to get any further capacitance. But with the structures printed on the cellulose nanofiber composite, we saw a gradual and continuous increase in the capacitance of the sensor as we increased throughout that relative humidity range. And specifically, we saw that this structures printed on the CNF composite exhibited a 45.8% increase in capacitance compared to just a 26.3% increase for structures from the cardstock over the same 39% change relative humidity. So we have greater sensitivity for structures printed on these CNF composite. Additionally, we saw that the impedance and self-resonance for structures printed on the CNF composite were lower than those printed on the cardstock. And again, this was 40% lower in the impedance and self-resonance compared to the structures printed on cardstock. And so this means that this helps prevent dequeuing the resonator, and so we have better performance from our sensor. So this is very promising. And so the conclusions were, the infusion of CNF solution into the surface of cardstock helps us polarize the otherwise rough cardstock surface and produce smooth surfaces with minimal amount of material usage, and that these substrates are suitable for combining with processes such as screen printing for printing electrical structures with high fidelity and repeatability. The CNF infiltrated layer, which we know to be hygroscopic, shows that it is moisture responsive, and this translates to the ability for us to detect ambient moisture changes, specifically in the 902 to 928 megahertz band. And more importantly, we saw that the self-resonant behavior of these structures on the CNF is well above the band. So we know that the response in our 902 to 928 band is purely capacitive, so that it's easy for us to back out what the moisture changes. And so we saw that this substrate therefore is suitable for passive RF applications. And again, since this substrate was completely made of cellulose, it is free of synthetic polymers, and so it can safely biodegrade, and so it's suitable for agricultural and other related applications. And with that, I'll finish my talk, and I'm happy to take any questions. Thank you.